Okay, so in this video, we are going to go into a beautiful journey of Fourier transform. Like we will basically introduce the Fourier transform from the ideas of Fourier series, but like we will actually start this video even from the very basics, even though you don't know what Fourier series is. I will try to give some ideas and then like we will slowly start developing our ideas and then go into Fourier transform at last. So we start with a simple question. So let's say if I want to take an infinite sum of cosines, right? So let's just say some constant and then cosine of 0x basically just 1 and then some constant cosine of 1x, some constant cosine of 2x, some constants cosine of 3x, and then goes and goes and goes and goes and goes on. So yeah, let us say that this result is some sorts of function, right? Okay. So now, like over here, notice that like let us try to observe some properties of this function. Okay. So we know that this has a period of 2 pi, this cosine function. And this has a period of 2 pi by 2, which is just pi. This has period of 2 pi by 3. Next has period of 2 pi by 4, and then so on, right? But notice that even this function, which has period of pi, will repeat after 2 pi, right? Even this cos 3x, which has period of 2 pi by 3, will again like repeat, okay, like, even if its period is 2 pi by 3. So there might be some 3 such repetitions in the interval of 2 pi. But again, after 2 pi, it is going to make the same repetition, right? So yeah, if we like look at all of them as a common function, all of them are going to repeat after 2 pi, right? So yeah, as a whole, this infinite series is going to repeat after 2 pi. So yeah, one of the properties that function has is the period of 2 pi. That means its behavior repeats after every 2 pi. Also, like since all of these are even functions, since all because they're even function, this function is going to be even, right? Yeah, so now we notice that like this infinite series song from k equals to 0 to infinity is sub k cos kx is going to give us a function which is even as well as has a period of 2 pi. Okay, now the thing is this is not interesting, but the interesting thing is not just this gives us a function which is even in 2 pi periodic, but the fact that any function, let's fx equals to x, fx equals to x square, not x, I mean only x square, any function which has period of 2 pi, definitely x square doesn't have period of 2 pi, but we can define a modification of x square, right, which has period of 2 pi, just like this, right? This becomes a pi and this has minus pi. So yeah, we can just like make a modified definition of x square, right? So the thing is that the interesting thing was, let's not get diverted from the topic. The interesting thing was any function which has period of 2 pi and is an even function can be written as this infinite series. Can be written as infinite series. So that's the interesting thing. Like, and when people like got this idea, like they would really want to develop this idea and then like progress with these ideas, and that's how Fourier series developed, right? And yeah, just like this, also notice that any function which has period of 2 pi, and is odd can be written as this infinite series, sum from k equals to 0 to infinity, some constants with sign kx, right? And this idea can be further developed. Like, let's say the function is neither even nor odd, but just has period of 2 pi, Now, this can be written as infinite series involving both sines and cosines. A sub k cos kx plus infinite series involve of when k goes from 0 to infinity of b sub k sine kx. And this was a really interesting idea that shook the world, like that got viral over the world. Now this can be modified a little bit. Now since now we require that fx has the period of 2 pi, we actually want the period to be anything, just a number t, right? Some time period t. So we can actually make that happen. to make a period of 2 pi, we can actually just change the period of the cosine signs, right? It's not that hard. If you want to make this cosine function to be t periodic, first of all, if I multiply that by 2 pi, now the period, I'm sorry, I did not write the cosine function at the beginning. I'm sorry for that. Okay, now if we actually first write over here k times 2 pi x, now its period changes from 2 pi to 1. We just divide by the number that we introduce over here. So since I introduced 2 pi, we just divide the actual period, which is 2 pi, by 2 pi. So the period becomes 1. And now if I divide this by t, the period becomes t. So the period of this new function, cos k times 2 pi by tx, has period of t. Similarly, I can introduce the similar sum b sub k and then sine k times 2 pi by t x. Okay, now yeah, so now this says us that any function with period 2 pi, also I forgot to mention something, that this function should also be piecewise continuous. Piecewise continuous. Yeah, I'm sorry for forgetting to mention that again. So now, yeah, we get the idea that any piecewise continuous function with period of time t can be written as this infinite sum, right? And yeah, definitely you can solve. Definitely, if you know the function, there are ways you can solve for these constants a sub k and b sub k. Yeah, but that's not the goal of this video, because the goal of this video is actually to introduce the idea of the Fourier transform from Fourier series. So we are not going to get over how to solve for a sub k, b sub k, right? You can just go that online. That's not too hard. Like, you just need to evaluate some integrals to find that, given that we know f of x, right? So yeah, you can do that on your own. But now let's go to like how we get the idea for this Fourier transform from here. Now, I guess you guys know the Euler's formula, right? Where e to the power I theta becomes cos theta plus I sine theta. And also, like now if you replace the theta by negative theta, e to the power I times negative theta becomes cos of theta minus I times sine of theta, right? From here, we can get the formulas for cos theta in terms of exponential. That is e to the power I theta plus e to the power minus I theta by 2. Similarly, we can get sine theta as e to the power I theta minus e to the power minus I theta by 2i, right? Okay. So now if you know this, now let's just try to substitute it back. So we see that now function with again a period of t, can be written as this infinite sum. Sum from k is equals to 0 to infinity, a sub k, and then now this just becomes e to the power I. Okay, now for the sake of simplicity, let us just define this 2 pi by t to be omega naught, okay? This omega naught, this just because angular frequency, this means the 2 pi by t, right? That means basically angular frequency means like how uh angular frequency means the amount of time it takes to make a rotation of 2 pi, right? Yeah. So yeah, now let's just replace that by omega naughts for the sake of simplicity, because it takes a lot of space otherwise. So I omega naught x plus e to the power minus I omega naught x by 2 plus sum from k equals to 0 to infinity b sub k. This is e to the power I omega naught x minus e to the power minus I omega naught x by 2i, right? Also notice that both of the sums are going from k equals 0 to infinity, so definitely we can merge them. So f of x, and yeah, this again has period of 2 pi, again has period of, I don't think I need to mention that again and again from now, I guess. Sorry, no, not 2 pi, period of t actual, I'm sorry. Okay, you understand that, I don't need to write it, okay? So yeah, that becomes sum from k equals to 0 to infinity. Now notice that if I merge it, this becomes e to the power I times omega naught x, And then yeah, if I merge it, I will have a sub k by 2 from here, and then b sub k by 2I from the other side, right? And yeah, and with e to the power minus I omega naught x, I will have a sub k by 2 minus b sub k by 2I, right? Okay. Now, notice that, uh, okay, so now notice that I will be breaking this two sums again. Okay, let me just break it again. There's some reason for doing that, which I will show you. And also before breaking that, like I will, what I will do is I will just evaluate the term for k equals to 0, right? For k equals to 0, this will just be to the power 0, which is 1. That's also to the power 0. In the second term, that's 1. And if we add these two, it just becomes a sub 0, right? Is that it? Yeah, it just becomes a sub 0. Now from 1, I will just divide this sum. So e to the power r omega naught x is sub k by 2 plus b sub k by 2I. And again, this also I'll write it as e to the power minus omega naught x a sub k by 2 minus b sub k by 2I. Why do I feel like... Oh, over here I forgot the k. While introducing I forgot to write the k over here. So let me write the k as well. I should not have forgot the k because that's an important thing. I should not be forgetting the k over here, k over here, k over here, the k over here. So yeah, f of x now becomes a naught plus, okay, so yeah, now I can write this as sum from k equals to 1 to infinity to the power I times k omega naught x and then a sub k by 2 plus b sub k by 2I. Now over here, I'm gonna write it as sum from k equals to 1 to infinity e to the power I omega naught x, and then I'll write it as minus k. And there's some reason for doing that. Okay, now the reason is, notice that while this k goes in the way like 1, 2, 3 up to infinity, this minus k just becomes minus 1, minus 2, minus 3, and it goes up to like negative infinity, right? So what I can actually do is write this as a naught plus sum from k equals to 1 to infinity of e to the power I k omega naught x sub k by 2 plus b sub k by 2I plus sum from minus 1 to minus infinity of e to the power I omega naught x k, right? Because k is now going from minus 1 to minus infinity, and this becomes a sub minus k by 2 minus b sub, I'm sorry, no, b sub minus k by 2I, right? Okay, so now if I do that, notice that now if I just define this new constant, let's say c of n, to be the n naught 0 for n is equals to, let's say, 0. And if I define this to be a sub n by 2 plus b sub n by 2I, if n is equal, if n is greater than 0, right, for positive numbers, and a sub minus n by 2 minus b sub minus n by 2I for n being less than 0 for negative numbers. Now notice that this, like this first term, like a sub 0, this a sub 0 is also of the form e to the power I times 0 omega naught x, right? So yeah, basically we have terms for all values or all values of k from 1 to infinity for k equals to 0, and also from negative 1 to negative infinity. So how we can merge these all three sums is that we can actually make a sum go from minus infinity to infinity. For all of them, we have this constant defined by this Cn, and then we have e to the power I and omega naught x, right? And this actually merges all of the Fourier series. This all of the complex terms in the Fourier series can be written in a such simpler way. So yeah, from here, okay, still this is a Fourier series, but now this Fourier series in complex exponential form. So now this Fourier series is in the complex exponential form, right? Over here, this was we call the Fourier series in the trigonometric form. But now the Fourier series is in the complex exponential form, right? Okay. So now, after again, we are still going to the idea of Fourier transform. Like now, we just showed that the Fourier series can also be done in this way. Now after this, let's say we want to find the value of this c sub n. So yeah, for that, what we actually do is, uh, yeah, we just multiply both sides by e to the power negative I m omega naught x, right? Yeah, there's a reason for doing that. Like, and integrate from integrate from. Now we know that this function a has a period of t, right? If I want to generalize this to any function, like what I can do is actually just for any function, like if it's just defined from minus t by 2 to t by 2, like in like everywhere else it's just the same repetition, right? So if it's just defined from in this like domain, then definitely it has period of t, right? So I can basically generalize this to every function to have period of t by just defining it from minus t by 2, and in rest of the place I can just leave it undefined. I can do that, right? So yeah, so if I do that, so and like since it's defined in this domain, now I can integrate both sides and integrate from minus t by 2 to t by 2. I will do this. This actually give me the value of c sub m from for any general m, and that's how we will find c sub n. And from there we get the idea how to define the Fourier transform. So there's a few more steps. So please be with me. Yeah. So let's integrate from minus t by 2 to t by 2. F of x and e to the power minus m omega naught x, and then dx. Over here, I can actually take the integral inside the sum, and also this c sub n is a constant, and also just take the uh integral of this thing over here multiplied with this e to the power minus I m omega naught x dx, right? So yeah, so this integral minus t by 2 to t by 2 f of x e to the power minus I m omega naught x dx. This will now become sum from minus infinity to infinity c sub n from minus t by 2 to t by 2. Now we know that this is the c to the power I and then n minus m omega naught x dx. Okay, now let's see this integral in a different way. So we know that this the cos of I theta is just cos theta plus sine theta, right? Yeah. Now this omega naught, I guess you guys still realize that this omega naught is actually just 2 pi by t, right? Okay, so this function is like e to the power I theta can be written as a cos and sine, right? And also, okay, also this omega naught is 2 pi by t, and we are basically integrating from minus t by 2 to t by 2, right? So the thing is, like, I'm just going to give you a big idea that, like, this cos and sines, except for in like except when the n minus m is basically 0. At that case, cos 0 is 1 and sin 0 is 0. So except in that case, all the other cases, if you integrate in the entire like period, these are going to go to 0, right? Except when this n minus m itself becomes 0. In that case, cos 0 is 1 and sin 0 is 0. So in that case, there will just be a real 1 for the integration, right? Except in all other cases, like when this n minus m is not 0, so basically in the entire domain, this integral is going to 0. So we are going to use that thing. So I just give you a big idea. So like, yeah. The thing is, now this n is going from minus infinity to infinity, right? So now, so only in the case where this n minus m becomes 0, so that means this sum actually uh, gets to n, which is the same as m. In that case, this integral will evaluate to, so the inside thing will be 1, and then if you integrate 1, that will just be t, right? So this integral evaluates to t. In the other case, the integral evaluates to just 0. So yeah, so this will become minus t by 2 to t by 2 f of x to the power minus I m omega naught x dx. So yeah, so basically what I told you is that, so only in the case when it's m, that will exist, that will also give the integral just t. So yeah, that is what I told you. And on other cases, it just goes to 0, so the other terms will just be vanished. I just gave a vague idea, but hope you can just search up some materials online and then you can get the rigorous proof. But yeah, that's not, we don't really require that to introduce Fourier series, so I'm not going over that a lot. Okay. So now we get this thing, right? So yeah, for getting any general term, let's say general term CFN, I can substitute m by n, and that gives me a general term. Okay, now we are really close to introducing the idea of Fourier series. So till now we got that, we understood that. So for any f of x, of period t can be written as this infinite series going from minus infinity to infinity with some coefficients and e to the power I and omega naught x, where omega naught is 2 pi by t, right? And this c sub n can be found out using 1 by t integral from minus t by 2 to t by 2 f of x e to the power minus I n omega naught x dx. And where this omega naught is just 2 pi by t. Okay, now the things get interesting. Now, like humans want to like also deal with the functions which are not really periodic. So basically, if they are not periodic, we can just say that the period is infinity. So it repeats only after infinity. That means it never repeats, right? So yeah, we actually want to let the time period go to infinity, right? So we wanna deal with such functions. Okay, now if you want to deal with such functions, right? Okay, now obviously if time period goes to infinity, this omega naught becomes really small, right? This omega naught becomes really small, right? And like this is so infinitesimal that since t is going to infinity, this and omega naught, like it seems like it's just a continuous variable. So what I basically do is we now just write it as a continuous variable omega, right? So because this is so small, and then now the change seems like continuous, so we just write it as a continuous variable omega. So, and what that does is now this c of n just becomes c times, now since n omega naught is omega, it just becomes omega by omega naught. Okay, now we'll just, okay, now we are just we will just be interested in this c sub n, right? So because the thing is over here, we are writing a function in terms of a sum, and like this term is basically a term involving some sorts of this angular frequency omega, and this basically quantifies how how much of this term involving omega is, right? So that's why we'll be interested in Cn, and then so we will look at this the second integral where we get the idea how to find Cn. So over here, let me just take this c t to the other side, and there's reason for doing that. Okay, so right now, what I just told you is that, so yeah, I just told you that this now behaves like a continuous variable, and so we are naming it as omega, right? Okay, now over here, this thing t times c. Now our, like, basically t is going to infinity, right? And now c is also a function of omega by omega naught, right? And this omega is really small. And over here, like, this will just be here, even though this t is be a really large number, but this will still just be a function of omega, right? And note that, like, I'm writing it in a different way, not the same f, it's different f. So yeah, when, like, the thing that happens when t goes to infinity is, now we will have this left hand side as a function of omega, and this integral goes from, now it goes from minus infinity to infinity, and then f of x. Now that just behaves like omega, right? Like, just a continuous variable omega. We just don't need any n now and dx. That's how it's defined, and we know that this f of omega has cn in it, like, and that gives us that also gives us the idea of how much of this omega is, like, I mean, how much this is the quantity involving omega, right? How much of that omega is in the function. So yeah, basically this f of omega basically quantifies how much of an angular frequency is in a function. So that's why this is important. So basically, this thing, the Fourier transform, basically, like, gives a function capital F omega that will give us how much of any angular frequency is in a given function f of x, and that's why it's important. So yeah, we actually use it in a lot of, in graphics and a lot of other fields, like where we have dealt with waves. And if you want to find out how much of angular frequency is there in a certain given function, we use this transform, and it's also helpful in solving PDEs, the partial differential equation, or a lot of other things. So I hopefully believe that this was a good introduction, and yeah. So we have derived it, right? Yeah, minus and minus infinity, yeah. To the power minus omega x dx. Yeah, we have derived it. So that was it. Hope you enjoyed the video. Thanks for watching, and I look forward to seeing you in upcoming videos too.